Okay, the monetary approach to exchange rate. The first assumption, we have two main assumptions. The uncovered interest parity condition, the purchasing power parity condition. The uncovered interest parity can be expressed as the interest rate equal to foreign interest rate plus the percentage change in the exchange rate. Okay? The purchasing power parity in log, which in absolute value is internal price equal to exchange rate which multiply foreign prices, can be also expressed in terms of logarithm as small pt, so the log of price, equal to st plus small p star, using the log. Okay? Now, so uncovered interest parity and purchasing power parity. We have these two assumptions. Then we have to consider the equilibrium in the money market, because this is the monetary approach to the exchange rate. So we assume that the income or GDP or consumption is exogenous. It's given by nature. Okay. So the equilibrium in the goods market using the log of each variable can be expressed as the nominal money, the log of the nominal money stock, small m, minus the level of price. This is the real money stock in log. Okay, is the log of nominal money stock divided by the level of price, which is the log. Okay, the real money stock is MT divided by PT. Okay, if we apply the log to this, we get log of nominal money stock minus the log of prices, applying the property, and this is equal to MT, which is the log of nominal money stock, minus PT, small pt, which is the log of price. So the real money stock is this, and we have the inequilibrium in the money market. The real money stock should be equal to the money demand, real money demand. And we assume that real money demand is linear. Okay? Is a linear function. It is equal to alpha 1, which is a parameter, which multiply the level of exogenous consumption, which is given in this model, minus a parameter alpha 2, which multiplies the interest rate IT. So applying, let me repeat again for people at home, okay? The real money stock should be equal to the real money demand if we apply the purchasing power parity and the uncovered interest parity. We get this equation, and from here we have the dynamic equation of the exchange rate in the monetary approach to the exchange rate. What we have to do is to have an equation, a relation between S dot T and ST. This is a differential equation in ST, in the exchange rate. And it's easy to get S dot T from this equation. as 1 divided by alpha 2, which multiply the exchange rate, minus 1 divided by alpha 2, which multiplies nominal money stock minus foreign prices plus alpha 2 foreign interest rate minus alpha 1 the level of exogenous consumption. So this equation gives us the dynamics of the exchange rate. This part of the differential equation, this is a differential equation in the exchange rate, okay? This part contains or includes all the exogenous variables. This part is exogenous. Nominal money stock, foreign prices, foreign interest rate, and the level of consumption is exogenous in this model. So we can call this part, omega t, and our differential equation that we need to solve becomes s dot t equal to 1 over alpha 2 st minus 1 over alpha 2 omega t. And we need to solve this differential equation. Solving this differential equation, we understand the dynamics of the exchange rate. So our differential equation is the derivative, the percentage change in exchange rate equal to 1 over alpha 2, the level s of t, minus 1 over alpha 2, which multiplies the exogenous force in this model. Now, the phase diagram can be used also in this case, because in this case we have an equilibrium solution for the exchange rate. Yes, it's enough to impose that s dot t is equal to 0, which implies percentage change equal to 0. So the equilibrium solution, we assume that is positive, and it's positive because the exchange rate is positive. Anyway, it's log, so maybe also it's negative. But if this is the equilibrium solution, and we put here s dot t respect to st, due to the fact that alpha 2 is a parameter greater than 0, okay, the phase diagram is an increasing function. So we can see that the equilibrium solution we can call S bar is globally unstable, as we have seen yesterday. But yesterday the money demand was an implicit function. Now we have an explicit money demand function which is linear. So we have dynamic instability because if the exchange rate is here, the exchange rate depreciate. Small s, okay? Because now we are considering the log, small s, okay? If the exchange rate is here, you have a continuous appreciation in the exchange rate. So this is globally unstable. This solution is globally unstable. Anyway, we will solve backwards the differential equation just to solve the model, but we know that we will need to solve it forward-looking, because if we solve backward-looking, we will get a solution which is globally unstable. So a solution in which if we have a difference between the initial value and the equilibrium value, you will go toward plus infinite or toward minus infinite. We know from the phase diagram. Okay? It's clear? And yesterday we have seen also the economic explanation of this dynamics, showing that if the exchange rate is greater, you have a reduction in real money stock, so an increase in interest rate, and so a further depreciation. Okay? Now I want to show you how to solve backward this model, and for the forward solution, which is really difficult, I will give the final solution. Okay? So it's an intermediate level. Okay? Okay. Now, how we can solve this differential equation? I write again the differential equation. The differential equation is s dot t, so the derivative of this with respect to time, equal to 1 over alpha 2, which multiplies st, minus 1 over alpha 2, which multiply the exogenous components, the exogenous variables. Now, to solve this, we know that we need to write this as s dot t minus 1 over alpha 2, which multiply st, equal to minus 1 over alpha 2, which multiplies omega t. Okay? This is the differential equation. We need to multiply both sides by the integrating factors. The integrating factors is, we know this. What is the integrating factors in this case? To multiply by the integrating factor, so it's e to the power of minus t over alpha 2. This is the integrating factor, okay?
So what's t?
T divided by alpha 2.
Alpha.
Yes, is the integrating factor. Now the problem is that we need to integrate these two sides of the differential equation by between 0 and t. So we need to change the variable. Okay? What I'm saying is now we need to integrate both sides of this equation, but because we need to integrate between 0 and t, because this is a backward looking solution, is a solution between 0 and t, from the initial time until now, from 0 until now. And this part becomes the derivative of S we call now time v, because t is the extreme of integration. So we need to use another variable, but it represents time, okay? So SV, which multiplies e to the power of minus v over alpha 2, this derivative with respect to v, we are applying the same rule we have seen for the differential equation. In dv, because this is an integral. Okay, the derivative, just to check the condition, the derivative of this function is, the derivative of the first is s dot v, which multiplies the second function, e to the power of minus v over alpha 2, plus the first function sv, which multiplies the derivative of the second function. But the derivative of the second function is the same function, e to the power minus v over alpha 2, which multiplies the derivative of the exponent, so which multiplies minus 1 over alpha 2. This is equal to, collecting e to the power of minus v over alpha 2, we get s dot v, okay, minus 1 over alpha 2 sv, which multiplies e to the power of minus v over alpha 2. So this is equal to this derivative. Now it's clear. This is quite clear. You can check to see the video at home. The second part is the integral between 0 and t of minus 1 over alpha 2, which multiplies omega v, because now time is v, e to the power of minus v over alpha 2 in dv. This is the other integral. So now, how we can compute the first integral? It's quite easy, because differential and integral are inverse functions. dv and dv simplify, okay? And we get, in the first part, sv, the exchange rate, which multiplies e to the power of minus v over alpha 2 between 0 and t. We need to compute this function between 0 and t, because this is the backward solution between 0 and t. And the second part is minus 1 over alpha 2, which is constant, so we can put outside the integral between 0 and t of omega v e to the power of minus v over alpha 2 in dv. The first side of this part is the value of this function on t, and the value of minus the value of the function on 0. So we have, I need to delete, we have st e to the power of minus t over alpha 2, which is the value of the function if v is equal to t, okay, minus s0 e to the power of 0 if v is equal to 0. And the right hand side is minus 1 over alpha 2 integral between 0 and t omega v e to the power of minus v over alpha 2, correct? Yes. In dv. Okay, perfect. So the solution of this exchange rate, try to understand this point. The solution will be st e to the power of minus t over alpha 2. This is 1, okay? E to the power of 0 is 1. So it's equal to S0 minus 1 over alpha 2 integral between 0 and t omega v e to the power of minus v over alpha 2 in dv. Okay? So we can get st as st equal to s0 minus 1 over alpha 2 integral between 0 and t omega v e to the power of minus v over alpha 2 in dv, which multiplies e to the power of t over alpha 2